And the results are consistent with the spinning or Kerr black hole. So right off the bat, there are a couple key features of this image that we can identify that are going to be very important later on. So first of all, we can identify, sorry, something isn't working. Okay, there we go. First of all, we can identify this ring of emission from hot plasma surrounding the black hole that causes this distinct ring-like appearance in the image. And we see that this ring is much brighter on the bottom, and that's due to Doppler boosting. So because the ring is rotating, the ring of emission is rotating, the bottom half gets Doppler boosted, while the top half gets Doppler deboosted, causing this brightness asymmetry. And the third important feature is this dark shadow in the center of the image, where the brightness drops dramatically. Now, this shadow is very important, so I want to take a few minutes to talk about where it actually comes from. So in order to understand the origin of the shadow and where this darkness comes from, we first have to understand where the light comes from. So the light reaching our screen in this image comes from the emitting plasma surrounding the black hole that's emitting primarily via synchrotron radiation. Now, the photons emitted from the plasma will follow trajectory, very specific trajectories. They'll follow null geodesics, which are governed by general relativity. And so we can plot the trajectories of these geodesics that connect the observer to the source. And when we do so, we find that there are two main classes of geodesics. So if we have our source, or if we have our observer shown as this radio dish here, and we have our source shown as a black hole with some accretion disk here, and we plot the geodesics connecting these two together, we find that there are two classes of geodesics. So some geodesics, like these, will pass through the emitting material and escape off to infinity. These rays will be very bright since they are long, they travel through the emitting material, and are therefore able to build in intensity before reaching the observer. On the other hand, there are geodesics that connect the observer directly to the event horizon itself. And because these rays terminate on the event horizon without passing through much of the emitting material, these rays are going to be much lower in intensity. And furthermore, they'll be Doppler deboosted often, since the material here will be falling onto the black hole. And so it's this latter class of rays that corresponds to the shadow. These rays that terminate on the event horizon and will therefore be much darker. And so this is why the central region of the image is much darker. So one question we can ask now is, what is the shape of this shadow? Meaning, if we take the black hole image again, and we try to draw the boundary that delineates geodesics that terminate on the horizon and geodesics that terminate on the at infinity, what will the shape of this boundary look like? So in general, this boundary forms a closed curve on the image that's called the critical curve. And the critical curve has a very distinct shape. The shape depends on two parameters: the inclination at which we view the black hole and the spin of the black hole, where spin is a dimensionless number normalized from -1 to 1 that indicates the black hole's angular momentum. So the critical curve, so here's a nice simulation showing how the shape of the black hole changes as we spin up the black hole, how the shape of the critical curve changes as we spin up the black hole. So here we'll see the spin, here we'll see the size of the event horizon, and here we'll see the critical curve changing shape as we spin up the black hole. And so as we see, as we spin up the black hole and increase its spin from 0 to 1, the critical curve goes from a circle to a more deformed shape that flattens on one edge and translates off of the center of the image. And so just to recap, this is the shape of this critical curve is really important because it tells us the behavior of rays fired backwards from the observer towards the emitter. Because if we imagine tracing geodesics towards the black hole, if the geodesic is traced from inside the critical curve, it will hit the horizon. And if it's traced from outside the critical curve, it will escape off to infinity. So this begs the natural question, well, what about geodesics that are fired from right on top of the critical curve, that straddle the boundary between the two? These geodesics have very strange behavior because rays fired backwards from the critical curve neither plunge nor escape. Instead, something in between will happen. These rays will asymptote to spherical photon orbits, meaning that a ray fired backwards from on the critical curve will asymptote to one of these orbits where the photon will sit at a fixed Fourier-Lindquist radius forever. like the orbits shown here. So we can ask, well, where do these orbits exist? So for Kerr black holes with non-zero spin, there's always a minimum Boyer-Lindquist radius and a maximum Boyer-Lindquist radius. And anywhere in between the two, one can get one of these bound null orbits, which is why this region of the space-time in between R min and R max is called the photon shell. And the photon shell contains these bound spherical orbits. It's worth noting, however, that we can't actually see the photons on these orbits because they're trapped. They'll stay on because they're trapped on these orbits. Instead, what we see are the photons that have been slightly perturbed from these orbits and can therefore escape off to infinity. So this is possible because the spherical photon orbits are unstable. That is, if you have a photon sitting on one of these orbits and you kick it radially outwards, it'll spiral off to infinity where it could be seen by some distant observer. So here's an example of what this kind of thing may look like. What we're looking at here is a black hole in the middle, a photon shown in green. It's traveling on this spherical orbit. And what we're going to do is we're going to perturb this orbit, kick it slightly radially outward, and watch it spiral off to infinity as follows. So we see that, well, it started on the spherical orbit. After you kick it radially outwards, it's going to spiral off. And in principle, if an observer were sitting up here, they'd be able to see this photon arriving at them. Now, we can quantify the degree to which this light ray is bent by counting the number of half orbits on the trajectory and labeling it with an integer n called the subring index. So in this particular simulation that we just watched, this would have an n of 3. Because 3 half orbits were completed. So we can watch one more time to see that happen in real time. So 1 half orbit, 2 half orbits, and then the 3rd half orbit before escaping. So this would be labeled with n equals 3. And so light rays with the same value of n form concentric rings on the image, which is why and so these rings on the image are called the photon subrings, and it's why this integer n is called the subring index. Each of these photon subrings behaves in a different way, and in particular, as n increases, the rings get exponentially closer to the critical curve, and they get exponentially thinner, so exponentially harder to resolve. Here's a nice simulation demonstrating what that looks like, and we'll see that as n goes from 0 to 1 to 2, the rays are going to be lensed and bent more and are therefore going to be pushed closer and closer to the critical curve. So we see that for higher order subrings, again, they'll get compressed into a smaller region of the sky that's closer and closer to the critical curve. And so when viewed together and we stack all of these contributions on top of each other, we see a bright photon ring shown here that forms near the critical curve. And so this tells us that an image can actually be decomposed into flux contributions from each subring, and then we can stack these contributions back together to reproduce the full image. That is, a total image of a black hole can be thought of as a sum of n equals 0 emission, so photons traveling along geodesics that completed 0 half orbits, plus n equals 1 emission, plus n equals 2 emission, all the way out to infinity. And each of these rings will be exponentially thinner, closer to the critical curve, and demagnified. Now, it's worth noting that there is some distinction on terminology that can be used here. we've been saying photon ring and photon subrings, but there are other ways to refer to these rings as well. So some refer to the low order subrings as lensing rings, or lensing ring, and a recent paper from Vincent and Wilgus uses the term secondary ring to account for the brightness that occurs specifically from the astrophysics. Okay, so now that we know where the photon ring comes from, we want to be able to simulate it and simulate images of the photon ring. And this in general is done in 2 steps. So first, we need to determine the conditions surrounding the black hole. And this is done using general relativistic magnetohydrodynamics, or GRMHD for short. So after we know the conditions surrounding the black hole, the plasma properties, the magnetic fields, from there, we can then take a picture using general relativistic ray tracing and radiative transfer. And this works in the following way. So in these ray tracing codes, an observer is set up far away from the black hole, and geodesics are then traced backwards through the space-time around the black hole, and radiative transfer is then integrated along these geodesics back up to the observer to determine the intensity along each ray. And this ultimately defines a simulated image of a black hole and works well for defining these images as seen by a distant observer. So ray tracing works really well, but there are resolution constraints involved. In particular, we need very high resolution images to see the subring structure, because as we said, the subrings get exponentially narrower towards the critical curve and therefore get exponentially more difficult to resolve. To put this in perspective, the Event Horizon Telescope maintains a library of ray traced images, and these ray traced images are all 160 by 160 pixels, and they span a 160 microarc second field of view. One such characteristic image at this particular resolution is shown here. Now, this particular image is a bit blurry, as we can see, and in fact, it's only good enough resolution to see the n=1 subring. If we fix 160 microarc second field of view, then to see the subrings of this image, we need 128 by 128 pixels to see the n=1 subring, which this picture does quite well, which this image does quite well. It's 160 by 160, so that's more than sufficient. But if we wanted to see the n=2 subring, we would need to kick up this resolution by a factor of nearly 20, hitting over 2000 by 2000 pixels in the image. And to see n=3, we would need to go even larger and get to over 32,000 by 32,000 pixels in this image. So we certainly cannot see n=2 or n=3 in this kind of image, just n=1. And so the bottom line is that if we want to probe the subring structure at values of n larger than 1, we have to dramatically improve the ray tracing efficiency. There is a beacon of hope here, however, because even though I've said that we need to improve the resolution by a factor of nearly 20, that's not entirely true. We only need to improve the resolution by a factor of 20 in one thin region of the image near the photon ring itself. If we could concentrate pixels near the photon ring and interesting features of the image while spreading out pixels very sparsely everywhere else, then in principle, we could achieve our goal. And so the question becomes, can we selectively choose where to concentrate resolution in the image? And this motivated the idea of adaptive ray tracing. So over the past year, I've been developing an adaptive ray tracing algorithm to make that does just this. It makes ray tracing faster by concentrating rays in areas of interest on the image, like the photon ring, the accretion flow, and in some cases, the jet. This is a project that I worked on with a number of different collaborators, including Ben Prather of the University of Illinois, and Michael Johnson, who's on this call. Additionally, and the way we approach this project is we modified the pre-existing ray tracing code IPOL to include an adaptive ray tracing component. And in doing so, we had a couple of key goals in mind. So first, we wanted to improve the ray tracing efficiency by concentrating rays in regions of the image with small scale structure, such as the photon ring and the thin arms of the plasma. Second, we wanted to probe the structure of the n=2 and n=3 photon subrings, because as we saw, the current EHG image library only gets n=1. And finally, we wanted to provide insight into the time evolution of small scale features in these simulations. We didn't want to just ray trace one snapshot and call it a day. but rather we wanted to ray trace large quantities of snapshots so that we could track these features over time. All right, so our algorithm worked in the following way. If we want to generate a high resolution image, we start by ray tracing this image at a low resolution on a uniform grid. So we might start, for example, with just 33 by 33 rays fired backwards on a uniform grid and computed to determine the intensity at each ray, giving rise to, at this point, a relatively blurry image. And it's blurry at this point because the rays are so sparsely spaced on this grid. But that's okay, because what we do in the next step is we go back and refine. Specifically, we choose to refine and concentrate rays where the spatial derivatives in the intensity are large compared to a pair of absolute and relative tolerances. If the spatial derivatives are large, this is indicative of fine structure or sharp features on the image that we would like to refine around and resolve more clearly. So we ray trace in these refined regions, and we interpolate everywhere else using nearest neighbor or linear interpolation. And we quantify the amount of interpolation using an interpolation fraction. At this stage, the interpolation fraction is 0% because every ray has been traced here. But what happens is that as we recursively enact this procedure, the interpolation fraction increases. So now kicking up the resolution by a factor of 2, we're concentrating rays towards the center of the image where we know the photon ring and turbulent accretion flow are believed to live. So we concentrate rays here, we keep rays sparse everywhere else. And so this leads the interpolation fraction to jump up now to over 50%. The process then repeats, now to 70%, process then repeats again, until finally we achieve a very large, a comparatively large resolution image. And that's possible because we've concentrated nearly all of the rays in the portions of the image that we want to resolve most clearly, namely the photon ring and the accretion flow. And in doing so, we were able to interpolate over 79% of the image simply by concentrating the rays we want in areas of interest. And this process works very well. It's accurate and efficient. And we were able to test so by testing our code on a number of different GRMHD and semi-analytic models spanning a range of parameter space. So we tested on black holes of different spins, inclinations, magnetization cuts, and electron heating parameters. And we found across the board that we were able to accurately reproduce images at over 10 times the speed. And in particular, we can show an example here. So here's a very high resolution, 4097 by 4097 pixels. This is an image that was ray traced non-adaptively, so using the old code. And here's the same image ray traced adaptively. These images the adaptively ray traced image is very accurate. These two images show a total flux that agree with each other to within a part in 10 to the 4. And yet it was ray traced at 10 times the speed. And again, that's possible because in the latter image, in the adaptively ray traced image, the ray density is concentrated in the portions of the image that we care about most, namely at the center towards the accretion flow and photon ring, where we're tracing hundreds of rays per microarc second squared. And in the outskirts, where it's dark and we don't care as much, we're ray tracing maybe 1 ray per microarc second squared. So now that we have this code and we've tested it and we showed that it works, we were able to use it and apply it to a number of different applications. So in particular, one such application is this idea of photon subring decompositions. So as we said earlier, a black hole image can be decomposed into a sum of contributions from individual photon subrings. And we were able to do this at unprecedented resolutions with adaptive ray tracing. So in particular, with adaptive ray tracing, we ray traced a simulation at 32,000 by 32,000 pixels over an 80 microarc second field of view. And at this level of resolution, we were able to resolve the n equals 0, n equals 1, n equals 2, and even the n equals 3 emission. So despite the fact that each of these subrings gets exponentially compressed into a smaller region of the image, with this level of resolution and with the adaptive ray tracing code, we were able to image each of these fairly well. And we found that when we stacked them back together, we were in fact able to reproduce the original image that we started with now as a sum of emission from n equals 0, 1, 2, and 3. Okay, so as an additional application of our code, we have applications to interferometry. So the Event Horizon Telescope as a radio interferometer doesn't take directly the picture of a black hole, but rather synthesizes the picture of a black hole. So just to go over and review how a radio interferometer works, it specifically measures the cross correlation between electric fields at two antennas. So if we have two radio antennas shown here, let's suppose they're separated by a projected baseline B, which we can write as the observing wavelength times a dimensionless vector U. The light surrounding the black hole will then give rise to electric fields that arrive with different phases and amplitudes at these two antennas. And in particular, the brightness distribution, so I of x, which is the image, is related to the Fourier transform of the correlation between these two electric fields. So written out explicitly, this says that, again, the cross correlation between E1 and E2 is nothing more than the Fourier transform of the image I of x. And in particular, the exponential that goes into this Fourier transform is that dimensionless baseline U. So this cross correlation, or just the Fourier mode, is the complex visibility. And as we see, the baseline U gives the Fourier mode, which tells us that a larger U, a larger baseline between two telescopes, measures higher frequency modes on the image. And so if we want to know what our black hole, what our simulated images look like to an interferometer, all we have to do is take a Fourier transform. So what is the Fourier transform of the photon ring? That's ultimately what we expect our interferometer to see. Well, in general, we know that the Fourier transform of a ring can be written as a sum of Bessel functions of the first kind, and will therefore have some sort of damped oscillatory structure. And we also know that higher frequency Fourier modes measure finer structure on the image. Since the finest structures on the image will be dominated by the higher order subrings, the very thin subrings, we expect that higher frequency modes will receive contributions from subrings with larger n. And so all of this together tells us that the picture we expect to see is something like this. So on the x-axis here, we're showing the baseline length U, which again is just the Fourier mode that we're actually sampling. And on the y-axis, we're showing the visibility amplitude, or just the Fourier amplitude. And so we see that each subring should give rise to these damped oscillations. And as we move out in Fourier space to higher frequency modes, we're going to probe a finer structure on the image and therefore measure contributions from higher order n. So we start out with n equals 1, then we receive contributions from n equals 2. As we go farther out, we receive contributions from n equals 3, et cetera, et cetera. So for reference, the current longest EHT baseline is order of 10 gigalambda out here, which means that we would not, for example, which means that we can resolve the n equals 0 and perhaps n equals 1 ring, but certainly none of these high frequency structure out here. It's also worth noting that observables can actually be directly extracted from this plot. So from the Fourier transform of the image alone, one can read off the period of this Fourier transform, which is directly related to the diameter. It's just inversely related to the photon ring projected diameter. And since the projected diameter of the photon ring is related to the spin of the black hole, in principle, one could extract observables like spin directly from this Fourier spectrum. And so it's useful for us to examine the Fourier transforms of our images. Okay, so let's see what happens when we do that with our adaptively ray traced images. If we take a high resolution image of a black hole that's adaptively ray traced, like the one shown here, and we take a Fourier transform along a horizontal axis, we see a very different picture than the one we saw in the previous slide. This does not look like a Bessel function. It doesn't have this nice periodic nature, but rather looks much more complicated and stochastic. Now, it's easiest to understand where the stochastic nature comes from if we decompose the Fourier transform into a sum of individual subrings. So here what we're seeing is the red curve is the Fourier transform of the total image. The green is the Fourier transform of the n equals 0 image. And the blue is the Fourier transform of the n equals 1 image. And now we get a much more clear picture of what's going on here. Because if we zoom in on this one region, we see that the blue curve, the n equals 1, shows that nice stamped oscillations that we expected. It does look like a Bessel function. It's the green curve, the n equals 0, that gets in the way and causes this stochastic nature. And specifically, it's getting in the way due to high power turbulence in the image, which introduces the fine structure and this noise at this relevant range of baselines. Now, the turbulence specifically occurs in the accretion flows due to magnetohydrodynamical instabilities. And the turbulence itself is very dynamically important. Because it transports angular momentum outwards, the turbulence is what allows accretion to occur in the first place. But even so, it does make it more difficult to see the structure, to see the signature of the photon ring in the visibility spectrum of these images. One way we can mitigate this effect, however, is by time averaging simulations. Because we expect that if we time average over many images, we expect the turbulence to get washed out, while the photon ring signature should be here to stay. It's not changing in time since it's purely a result of strong lensing around the black hole. So what we do is we use adaptive ray tracing to time average over high resolution image simulations, because this in principle should allow us to see the signature of the photon ring emerge in Fourier space. And that's exactly what we find. So again, just bringing up this Fourier spectrum of a single snapshot where the blue and the green are fighting against each other and cause this very stochastic signature to arise in the red. What we do is we repeat the same procedure, but we use adaptive ray tracing to generate a host of snapshots and then time average over 500 GM over C cubed. In the case of M87, this is about 5.5 months. And when we take a Fourier transform of the time averaged image, we get a much more different picture. In particular, we see that if we zoom in on the same region, the blue curve stayed the same as we expect, but the green curve, the n equals 0 emission, has been dramatically suppressed by many orders of magnitude in amplitude. And that's because, again, as we time average, the turbulence is going to get washed out. And so the same high power noise that we were seeing earlier is being batted down. And this allows the blue curve to rise up and dominate the visibility spectrum in this range of baselines, which is why the photon ring signature can now be seen much more clearly. And this is important because these kinds of studies tell us the timescales over which accretion turbulence varies in these images, in these simulations. So by studying how long it takes this green curve to be batted down, we can understand the timescales over which turbulence varies in these simulations. All right. Now, up until this point, we've sort of ignored a couple of complicating factors in a complete analysis of gravitational lensing in these images. So one thing we've ignored is the effect of different observing frequencies, because up until now, we focused exclusively on images that are ray traced at 230 gigahertz. So every image I've shown up until this point has used the same observing frequency, 230 gigahertz, because this is the observing frequency of the Event Horizon Telescope, at least up until now. However, a complete analysis of the photon ring has to include other frequencies. And this is because other frequencies will give rise to different optical depths of the medium and will therefore give rise to completely differently looking images. In particular, if there's high opacity, high optical depth in the medium, then photons will be attenuated before they can complete many orbits, which means that we won't be able to see high order subrings since they'll be extinguished. On the other hand, in the optically thin limit, we'll be able to see many subrings because photons can travel through the medium without being attenuated. And so I've been working on quantifying this with Maciek Wilgis, and we've been using adaptive ray tracing to ray trace over large quantities of high resolution images to extract the frequency dependence of the photon ring flux. So to give an example of what this looks like, if we now move to 86 gigahertz, which is more optically thick, we see that the photon ring is relatively dim, compared to the background emission. Because when we compare this to 230 gigahertz, which is more optically thin, and we plot it on this, excuse me, and we plot it on the same color scale, we see that the photon ring is significantly brighter in the 230 gigahertz image. And again, this is because at 230 gigahertz, the medium is more optically thin, so photons can travel through the medium more without being attenuated. And so this allows the signature of the photon ring to be brighter. And we generalize this to a range of different frequencies, not just 86 and 230. And we see that, as we expect, the photon ring becomes brighter at higher observing frequencies where the medium becomes more optically thin. So specifically what I'm showing here is on the x-axis, we have the observing frequency nu in gigahertz, shown from 86 gigahertz down here all the way up to a terahertz here. And on the y-axis, we're plotting the flux in the n=1 subring over the sum of the 0 flux and the n=1 flux. So essentially the relative flux contained in the photon subring. And we see that as we get to higher observing frequencies and reduce the optical depth, that subring is going to pop out much more clearly and is going to be responsible for a larger portion of flux in the image, as can be seen very dramatically between these two photos. All right. Now, another thing we've ignored up until now is the role of polarization. So far, we've only been looking at unpolarized images. We've only looked at images of the total intensity, but that's insufficient to get the whole picture because lensing and curvature and all these effects we've been discussing, they affect polarization too. In fact, polarization is uniquely affected by curvature because the polarization vector itself is parallel transported through the space-time. And so by studying polarization, this provides us with yet another opportunity to study the types of relativistic signatures that show up at high resolution. Now, one way we can incorporate polarization into the picture is simply by doing adaptive ray tracing with polarization, as can be shown in this image here. So this is the same idea. This image was adaptively ray traced and therefore able to achieve high resolution, high effective resolution. But now we're also showing these tick marks, which show us the orientation of the electric field vector at each position on the image. So we're incorporating polarization into the mix. And polarization is particularly important to study right now because the Event Horizon Telescope now has the ability to observe black holes with full linear polarization. So what started off as as this blurry unpolarized image that was released in 2019 has since been upgraded as of a few months ago to an image shown in full linear polarization, where here it's the same image, but now shown with these tick marks whose length corresponds to the polarized intensity of the image and whose orientation tells us the orientation of the electric field. So we're incorporating the linear polarimetric data. Now, if we want to understand these images, however, it's a lot more complicated than just looking at total intensity. And that's because when it comes to polarization, there are so many different factors at play. There are Faraday effects, the magnetic field plays a role. As we said already, the geometry will play a role, and many others as well. So it's a lot more complicated to tackle the problem of polarization than unpolarized images alone. And so we have to ask, well, how can we disentangle all of these different effects so that we can understand polarization from a very simple and uncomplicated point of view? Now, one way to do that is to use toy models. So in particular, one could use a toy model of equatorial emission, localize all of the emission to the midplane. And this would reduce, because toy models can help disentangle all of these different features. So one such example of a toy model was published just a couple months ago, or just last month actually, in a recent paper led by Ramesh Narayan, which developed a toy ring model for polarized equatorial emission in the Schwarzschild geometry. So the way this ring model worked is that an observer, very simply, an observer is stationed far away from the black hole at an inclination angle theta. a ring of matter is placed a distance r away from the black hole, orbiting at some velocity. There's a magnetic field, and the question is simply, what is the polarized appearance of this ring? And so this kind of simple toy model can elucidate many questions about how polarization actually behaves. And so in a project that I've been working on with a number of collaborators, we extended this toy model for the short shield model to the general Kerr metric. So in doing so, we were able to investigate the effects of spin on polarization and understand polarized images from yet another point of view. And so I want to talk about this toy model for spin in a little bit more detail. So we kept the same model set up as the one used in the short shield paper, where we place an observer far away from the black hole, place a ring of matter orbiting around the black hole, and ask what the polarized appearance looks like. And we make the following additional assumptions to help keep the problem a bit more tractable. So first, we assume that all emission is equatorial. Second, we assume an axisymmetric fluid and magnetic field configuration. Third, we assume that the emission is purely synchrotron with no other radiative processes. Fourth, we assume that the medium is optically thin with no self-absorption. And finally, we assume no plasma propagation effects like Faraday rotation. And so by making these assumptions, we're able to achieve our goal of isolating the individual effects on polarization and understanding how polarized images come to be from a bit more of an intuitive and qualitative point of view. So once we have these assumptions, we then go through the calculations to compute the polarized image of a black hole. And in doing so, there are 3 steps that are necessary. So first, we calculate the starting and end points of null geodesics that connect the observer to the emitter. And we do this using conserved quantities, since as is generally the case in physics, the presence of conserved quantities makes computations much easier. So the Kerr metric has 4 conserved quantities. There's a conserved mass, which in the case of light is just 0. There's a conserved energy associated with each null geodesic, a conserved angular momentum, and finally a conserved Carter constant, which doesn't really have a clear physical interpretation, but it is conserved. So once we compute the trajectories of these geodesics that connect the observer to the emitter, we then calculate the intensity delivered to the image along each of these geodesics. And we do that using properties of synchrotron radiation, and we also incorporate Doppler effects. Finally, the third step is to calculate the polarization pattern on the image. And this is done using the Penrose-Walker constant, which is yet another conserved quantity of the Kerr metric that encodes how the polarization vector is parallel transported. It's worth noting that the first step does require some light numerics, but the second 2 steps, steps 2 and 3, are fully analytic and therefore allow us to very efficiently compute these polarized images of a black hole. All right, so let's take a look at what this toy model, what kind of results this toy model gives. So one such sample configuration would be a face-on theta equals 0 inclination black hole. We put a ring of matter a distance 6 gm over c squared away. We endow it with the toroidal magnetic field, and we let this material spin clockwise on the sky to be consistent with M87. So our toy model predicts the following results when we have a non-spinning or short shield black hole viewed with this particular configuration. So here, what we see are tick marks whose length encodes the polarized intensity and whose orientation encodes the direction of the electric field vector at each position on the image. And the results we see here are exactly what we expected. The magnetic field is toroidal, and synchrotron radiation tells us that the orientation of the electric field should be perpendicular to the magnetic field, in this case, radially in and out. So this is exactly what we would expect. Using our toy model, however, we can then compare the figure we just saw with the high spin black hole so that we can isolate the effects of spin on the polarized image. So here now what we're seeing is a set of 2 ticks. In red, we see tick marks for the polarization pattern of the short shield black hole, spin 0. And in blue, we see tick marks of a highly spinning Kerr black hole, so a spin of minus 0.99. Now, despite the fact that these two spins are very different, the tick marks do not look that different. They almost perfectly line up. And it's only after we zoom way in on one of these ticks that we can actually see, okay, yes, there is some distinction between the two, but it's very small. The small distinction is due to frame dragging. So because the black hole is spinning, it drags inertial frames, and therefore will cause the polarization vector to rotate with it. But this effect is subleading, and in fact, we're able to quantify this by showing that the effect of spin is order 1 over the emission radius squared, meaning that by an emission radius of 6 GM over C squared, the correction is already order 1 over 36, which is quite small, and is the reason why these two ticks looked almost identical. That picture changes, however, if we look at the polarization of the subimages. So if we look at the n=1 subimage and isolate photons that have completed 1/2 orbit around the black hole, as opposed to 0, we get a very different picture of what's going on. So here, what we're looking at is the same field configuration, the same distance, 6 GM over C squared, but now we're looking at the n=1 subimage, and we see that the distinction is much more pronounced between the red and the blue ticks. And that becomes even more so if we zoom in as before. In fact, we're able to show that the change in the EVPA as a result of spinning up the black hole is order unity in the subimage, as opposed to order 1 over the emission radius squared in the case of the direct or n=0 image that we saw in the previous slide. Now, intuitively, this makes sense. When we look at the photon ring, when we look at the photon subring, we expect the geodesics to be more strongly lensed, and so the effects of frame dragging will become more pronounced, which is why you get a much bigger distinction between the low spin and high spin black holes. Okay, so now that we have an understanding of how polarization is affected by these various different factors, we can apply this toy model, as we did with adaptive ray tracing, to a number of different physical phenomena. The first such application of the toy model comes from hotspot modeling. So we know that polarized flares from hotspots are observed in the submillimeter and near infrared near the galactic center, Sagittarius A star. And we can apply our model very naturally to these hotspots. So there's work on this that's been done before. And in particular, here's a nice simulation from Avery Broderick and Avi Loeb showing what we expect the light curves of these hotspots to look like. And using our toy model, we can repeat a similar analysis and use our toy model to predict the polarization patterns of these flares simply by treating the hotspots as point-like emitters in the equatorial plane. And when we do that, we're able to get a very intuitive picture for what the polarized appearance of these hotspots look like. And in particular, we're able to generate a picture of what their polarization patterns look like, decomposed into n=0 and n=1 emission. So here we can play a movie that was generated using nothing but this simple toy model that shows us the polarization tick for n=0 and n=1, and the degree to which they're offset depends on the time delay between n=0 and 1, where this time delay occurs due to the fact that the n=1 ray has to travel for a longer period of time before reaching us. All right, so we see from these kinds of movies that using our toy model, we can get very simple pictures to isolate the effects of various parts of the polarization to determine how these polarized images are affected. And we're able to do so for both the direct and indirect images. and we see the differences between the two. We're able to then take these kinds of movies and we analyze them a bit more quantitatively to determine features of the magnetic field. And in fact, we validate and confirm analytically previous results about the stark distinctions between vertical and equatorial magnetic fields. So we find that vertical magnetic fields produce very different polarization signatures from equatorial magnetic fields when it comes to viewing these hotspots. And so by viewing the polarization pattern of a hotspot, and one could in principle determine the degree of verticalness of the magnetic field. One can also set inclination constraints on the black hole by looking at the polarization patterns, since as one transitions from low inclination to high inclination, the polarization pattern will undergo a very dramatic change as well. And so using our simple toy model, we can apply these to real life phenomena and understand how to interpret polarimetric observations of black holes while isolating these various complicating factors from one another. So in conclusion, we've developed several different models for analyzing these high resolution properties of black hole images. So we started out with the EHT with a very blurry image of a black hole. And we now have the numerical and analytic tools to understand the relativistic signatures that show up at extremely high resolutions and give rise to photos or to simulated images like this one. So we did this using an adaptive ray tracing mechanism that enables efficient computation of high resolution images and allows us to probe the photon subring structure as well as the structure of the turbulent accretion flow, both of which are dynamically important and contribute to to the structure of these lensed images. In addition to the adaptive ray tracing and GRMHD, we also have much simpler toy models that can elucidate these physically accessible relativistic signatures that go beyond just total intensity and include factors like polarization that would ordinarily be very complicated to study. Using these two models, we have applications to black hole images and time-dependent and time-domain phenomena, such as hotspots that are observed in real life in places like the galactic center. And in the future, there are a number of directions we can go from here. So we might, for example, generalize the work here to include alternative spacetimes that go beyond just the Kerr metric. And we might additionally include applications to instrumentation and space VLBI so that we can better develop missions and better develop instrumentation to be able to see things like the photon ring in the future. I would just like to say that if you're interested, the adaptive ray tracing code is publicly available. Here's the link to my GitHub. You could also feel free to shoot me an email afterwards. And I'm happy to provide any information about that. And I would just like to say thank you so much once again for having me. It's a pleasure to be here and I'd be happy to take any questions.
Okay, thank you very much.
Sorry, super quickly, I totally forgot. Would just like to acknowledge a couple people. Harvard SAO members, thank you so much to Maciek, Michael, Daniel, Mina, and Ramesh, and to the UIUC group, specifically Ben and George. But thanks again, and I'm happy to take questions.
Okay, thank you very much. I'm going to clap on behalf of the others. And if there are any questions, please. Oh, Deborah? Oh, that's not a question, that was clapping of the hands.
I'm clapping.
Yeah,
Hello.
Sorry. Thank you.
Hello.
Hello.
Maybe I have a question, but it might be just about the code. If you have this very, very large resolution of the ray tracing code, do you also need a very high resolution of the MHD simulation or?
Yeah, so that's a very fair point. And it's something that I think we do still need to investigate in a bit more detail, the, sort of limits of how much you're limited by the actual cell size in the MHD simulation. In general, we have developed some ways of interpolating between cells that makes the output image a little bit more accurate, even if you are limited by your fundamental cell size. But it's a very fair point that at the end of the day, you are still going to be limited by the resolution of the GRMHD simulation. And it's something that ultimately does affect our images.
Thank you. Because I was thinking if you have, if it makes sense or not, because I know especially with high spin values, the little change of the position of the ray ends up with on a completely different part of the simulation itself. So I wasn't sure if it makes sense or not. Also, if you were talking about time averaged simulations and time averaged data, are you using this slow light approximation or no fast light approximation or not?
Yeah, so all the images shown here were in fast light. Ultimately, we would like to be able to extend this to slow light, but that's certainly a goal for the future. Yeah.
Yeah. Okay. Thank you.
Thank you.
Thank you very much. It was very interesting.
Thank you.
Okay. There was a question in the comments whether you can show the link to your GitHub. So it was too quick to copy that. Okay.
So I have a question, Zach. What is your opinion? Do these two operations, it's kind of inspired by what Deborah said. Do these two operations commute? Meaning, if I take GRMHD simulation, I average GRMHD simulation, I ray traced averaged GRMHD simulation, versus I ray trace bunch of snapshots from time variable GRMHD simulation, and I average ray traced snapshots. Is that the same thing?
That is a great question. I think if you did this, and I should do this because this is a really interesting question. I think if you did this, they wouldn't be the same thing because of nonlinearities that occur from the interpolation as you're ray tracing geodesics through the individual cells. But I would say probably not, but I would have to imagine they're very similar. Yeah.
Right, and this sort of GRMHD resolution study, did anybody look into that? Like, you know, repeating, or really maybe not even repeating, but maybe first regrading simulation, like having one high resolution GRMHD simulation, regrading output on, you know, decreasing the resolution by, I don't know, factor 2, factor 4, and doing this studies of the ray traced image.
Yeah, so we did do that. We tested these images on lower resolution GRMHD simulations, and we found in general that it did not make much of a difference, particularly in visibility space. It almost showed the exact same signature, which was certainly reassuring and I think a nice sanity check. But going in the other direction, going to higher GRMHD simulations, there aren't that many available, so that's been the more difficult end to check.
Right. Let me ask a last one. So you give us those criteria for resolving or for imaging zero, first, second, third order photon ring. So what do these criterions really mean? Because it's like it's one thing to have one pixel in those higher order rings,